Welcome to video lecture F11. This one is on constrained optimization of quadratic forms. I'll be your anchorman, Tom Roby, and here are the outline and objectives. As you know from your calculus courses, maximizing and minimizing is a major application of mathematical modeling. And here we're going to solve specifically problems in constrained optimization where they can be cast as finding the maximum or maybe minimum value attained by a quadratic form on a set of unit vectors. So take a look at these pictures of what's going on. You see, over here I've got the unit circle, right? This is the set of all points x1 squared plus x2 squared equals 1, or things of whose norms have length 1. And it's a little hard to see, but you can see there's also its image on that parabolic surface, right? The green circle that goes around like this. So that's the set of values that we're trying to maximize or minimize. Because on all of you can think about this quadratic form as just being a function. It takes a point in R2 and it gives you an output in R1. So it gives you some kind of a height and you say, well, what's the maximum height? Now for something that's going out to infinity, there's going to be no maximum. But if we constrain it to only be points on the unit sphere, or circle in this case, then we will get maximum and minimum values. And so for each of these you can see that there's the image of the circle. I haven't put it in the domain in the other ones, but you see the image of that circle in all four of these quadratic forms whose pictures we've already seen in earlier video lectures. So let's remember what it means to be a unit vector. There's actually 4 different algebraic ways to describe this. So we can say that the norm of x is equal to 1, but that's the same thing as the norm of x squared being equal to 1 because norms are always positive. And that's the same thing as saying that the dot product of x with itself is 1. In other words, x transpose x equals 1. And if you expanded it out into coordinates, you'd be saying x1 squared plus dot 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 plus xn squared equals 1. And you probably know that that describes the set of points that do that form a unit sphere in whatever dimensional space you're at. So if we move this up a dimension, we'd be thinking our domain would now be all of R3, and we'd be thinking about where on the unit sphere is this quadratic form maximized or minimized. Okay, so now here's the key idea. It's easy to maximize a quadratic form when there are no cross terms. We'll see that in just a minute. And so we can leverage the principal axes theorem, which we've already seen, to take any arbitrary quadratic form, use a change of variables to make it a quadratic form with no cross terms, and then it turns out that the max constrained value will be the largest eigenvector of the matrix. So the actual value, the largest value that you get, is the largest eigenvector of the matrix corresponding to the quadratic form. And it turns out that we can also describe smaller eigenvalues of A as the maximum value on the quadratic form where we add some additional constraints. In addition to being on the unit sphere, it has to be perpendicular to some of the other maximum you've already found. Notice on these pictures, because it'll come up in just a minute, that the value of the quadratic form is indicated not just by the position, but also roughly by color, right? That the red points are the hottest. Those are the maximum values that you see, and the blue ones are the coldest. So another way of thinking about this is, you're looking along this quadratic form and you say, okay, so where am I the reddest along that quadratic form if you want the maximum? And so let's take a quick look at a specific numerical example. Right, so here I've got a quadratic form. It inputs a vector in R3. It outputs a real number. And so I want to think about this exactly as in all of R3 I'm assigning something. You can think of it as a temperature. And I'm asking, where is the hottest temperature going to be on the unit sphere, right? The set of unit vectors. So that's what subject to x transpose x equals 1 means. And what I'd like to convince you of is that this is actually a really easy problem when we have a quadratic form with no cross terms. And the reason is that you know that 7 times x1 squared, you know that the quadratic form 7x1 squared minus 5x2 squared plus 4x3 squared is less than or equal to, well, if I just replace all of these coefficients with 7, that'll definitely be bigger, right? This will be 7 times x1 squared plus x2 squared plus x3 squared. Okay? But x1 squared plus x2 squared plus x3 squared is equal to 1 because this is a unit vector. Okay, so since this is equal to 1, that means that this is less than or equal to 7. On the other hand, I can surely attain 7 for this quadratic form just by plugging in 1, 0, 0, right? I get 7. So since 7 is attained by the value 1, 0, 0, attained at 1, 0, 0, I'll write it in that form just to save vertical space. So 7 is allowed at 1, 0, 0. So that means that this quadratic form can't be any bigger than 7, but it definitely attains 7, so that has to be the maximum. Now, if you do the exact same reasoning the other way, you'll see that this quadratic form has to be at least minus 5 times x1, x2, x3. So the minimum value of this is going to be minus 5. And this is just the value of the largest eigenvector of the corresponding matrix, and this is the value of the smallest eigenvalue, because, right, what's the corresponding matrix? It's just 7 minus 5, 4, and then everything else is zeros, right? It's just a diagonal matrix in the case where you have no cross terms. Okay? So this is a simple idea, but it turns out to be key in what we're doing in the following things. So here's the theorem. If you want to optimize a quadratic form on a set of unit vectors, what do? You start with a symmetric matrix, which represents your quadratic form. We know that there's a one-to-one correspondence there. And you let m be the maximum value on the unit sphere. You let m be the minimum value on the unit sphere. Then m is just the greatest eigenvalue, lambda 1, and little m is the least eigenvalue, lambda n of a. Usually we'll organize our eigenvalues so they go from largest to smallest. That'll come up more specifically later. And then how do you get where are these things attained? Usually when you want to find out, you want to know not only what the maximum and minimum values are, you also want to know where they're obtained. But they're obtained by just setting x to be the corresponding unit eigenvector, because if you have an eigenvalue, you must have a corresponding eigenvector. And so you look at the unit length one. You just normalize it if you need to. Okay? So this is a simple but very useful result. And let's see what I want to say about the proof. So the proof is exactly leveraging what we already know, which is that any real symmetric matrix can be orthogonally diagonalized. Right? You can write it as P, dP inverse, where P is an orthogonal matrix and D is a diagonal matrix. And that's going to be the change of variables matrix that eliminates the cross terms in Q. Okay, so that's good. And now let's think about this, right? You have x is equal to Py. So what does that mean for x transpose AX? Well, if you plug that in, you'll see that it's y transpose dy. We've already seen this in a previous video lecture. And more importantly, what about the length of the vectors? Well, the length of the vector x squared is just x transpose x. And that's Py transpose Py. And now I have some dot, dot, dots, but maybe I'll fill in the dot, dot, dots for you. Right? So this is what? If you just do Py transpose, that's going to be y transpose P transpose. And then we have P, and then we have y, right? So now if I think about this P transpose P, this is an orthogonal matrix. So P transpose is the same thing as P inverse. So this is just equal to y transpose y. And that's equal to the norm of y squared. So this chain of equalities shows me that the norm of x squared is equal to the norm of y squared. So if I'm only interested in maximizing on things whose norm is 1, I mean same thing as whose norm squared is 1, that's the same thing as the set of vectors y whose norm is 1. So when I do this change of variables, it doesn't change where the unit sphere is. That's a way to think about it geometrically. All it's doing is, moving the unit vectors around. But if I'm only interested in the max or min, then the maximum value looking in terms of x will be the same actual value in terms of y. And you'll just be, and it'll happen at an eigenvalue because that's how this works. So, right, so like up here, when you're in the place where it's diagonal, then 1, 0, 0 is exactly the eigenvector corresponding to 7. And when you multiply this by 1, 0, 0, you'll get 7, the maximum value. Okay, so right, so it's just a combination. So the whole proof of this theorem is just a combination of using the principal axes theorem and using this easy observation that when you have no cross terms, all you have to do is look for the largest coefficients, right? The largest coefficients in the diagonal matrix turn out to be the same thing as the largest eigenvalues. Okay, so let's take one more example now. Suppose we wanted to find the max and min of this quadratic form, which is not diagonal, corresponding to a diagonal symmetric matrix that has cross terms. Well, so I guess what I want to do then is first of all figure out what's the corresponding matrix. So we've already actually looked at this example in a previous video lecture, and so you won't be surprised probably when I write down the matrix here, which is 1, 1, 3, 1, 3, 1, 3, 1, 1. Okay? So this is a matrix we've seen before. We know how to compute its eigenvalues and eigenvectors. So the eigenvalues are so lambda 1 equals 5, lambda 2 equals 2, lambda 3 equals minus 2. Oops. I'll write that down here. Lambda 3 equals minus 2. So by the theorem, if I want to know what the maximum value is of this quadratic form, well, it's just the largest eigenvalue. It's just this value 5. And if I want to know where it happens at the eigenvector. Now, the eigenvector corresponding to 5 is really easy to figure out because you notice that all of these row sums are the same, right? So whenever that happens, you just multiply a times 1, 1, 1, you'll get 5, 5, 5, which is 5 times 1, 1, 1. So clearly, this is the eigenvector corresponding to 5. And you can check if you want that, so this is 1, 1, 1 is the eigenvector, but it's not a point on the unit sphere, right? So if I want to figure out where this happens subject to that constraint, I have to normalize this to get a unit vector. So that implies that the vector that I'm interested in here is, I'll call it v1, is equal to 1 over the square root of 3, 1 over the square root of 3, 1 over the square root of 3. And you can check pretty easily that if you plug 1 over the square root of 3 in for each of x1, x2, and x3 here, that you actually get the value 5. Notice that you've got these square roots here, but they're always coming in pairs, so you're always going to be canceling them. So this will be a third, this will be 3 times a third, this will be a third, and so on. So you should double check that, pause the video if you like to make sure that that's working the way you want, that you agree with me on that. And now, if you want the minimum value, well, it's the same thing, right? So the minimum value here, maybe I shall circle this in blue. Since it's the coldest one, this is going to be the minimum value. And it's going to take place at the eigenvalue corresponding to minus 2. And I'll just tell you that, so I'll call this V3. Turns out to be, let's see. I'll just write it this way. 1 over the square root of 2 times negative 1, 0, 1. Okay, so that's the unit vector. Okay, so that was all very straightforward and a nice application of this principal axes theorem. And now we'll see how to leverage it further to figure out how to think about the other, like what this lambda 2 equals 2 means as an eigenvalue in terms of optimization. And ultimately, we'll actually be leveraging this whole discussion to get at the singular value decomposition in an upcoming lecture. Okay, so now let's see what we can do when we have a situation where we might have additional constraints and it'll allow us to interpret other eigenvalues of the matrix corresponding to the quadratic form. So here's the big theorem. It looks like a lot, but a lot of it is just saying things that are easy to understand, so don't be put off by it. This is all stuff we're familiar with, right? We want A to be a symmetric real matrix, corresponds to a quadratic form, and that quadratic form can be orthogonally diagonalized as P dP inverse, just like before. Now, without loss of generality, I want to assume that the diagonal entries of D are in decreasing order. In other words, that the largest eigenvalue comes upper left and then goes successively down until you get to the smallest eigenvalue. Okay? We know the things on the diagonal will be the eigenvalues. And that means that the corresponding eigenvectors, P will then be, I mean, if they weren't, you could always just rearrange, transpose some columns in P to make that happen. So there's no loss of generality there. So ui is going to be the eigenvector corresponding to lambda I. So all of that we understand. Those first 4 lines are no big deal. Now here's what's new. Suppose I want to maximize this quadratic form subject to not only do I have to be on the unit sphere, that's what the first constraint is, but I have to be orthogonal to the direction of the largest eigenvalue. Right? So you can imagine that happening. For some reason, you no longer, you can't go in that direction. The road in the direction of your largest eigenvalue is blocked, and you can only go in ways that are in the orthogonal complement of it. Right? Well, if you want to do that, so just imagine that k equals 2 here. So you'd have 2 constraints. You'd have the sphere constraint, and then you would have, it has to be orthogonal to the first eigenvector. Well, then the maximum value that you get for that is just lambda 2. It's just that second eigenvalue. Okay, and then suppose you say, OK, now I can't go in the direction of lambda 1 or the direction of lambda 2. I have to be orthogonal to that. So if my value x has to be orthogonal to u1 and u2, then lambda 3 will be the largest value, the maximum value. And it will be attained on the corresponding eigenvector. Okay, so we've got this great interpretation of what all the eigenvalues and eigenvector pairs are doing in this situation where you have any real symmetric matrix. Okay? So if you have k minus 1 such constraints, then the maximum value is attained by the eigenvalue lambda k when x equals u sub k. Right, so another way to visualize this geometrically is before we were maximizing our quadratic form on the unit sphere in R3, say. Now, if I have to be perpendicular, say, to the x-axis, then what I'll end up with, if I'm perpendicular to this, I'll end up with all the points on the circle, right? If you want to think about it as the plane perpendicular to that unit vector, just slices the sphere through the middle, and that great circle is what you're now maximizing on. So really all you've done is you've cut the problem down by a dimension. And that's actually how the whole proof works. So let's take a quick look at this example because it's very helpful, right? So if q of x equals the same quadratic form we happened before, subject to being on the unit sphere, and I have to be orthogonal to u1, well, so in this situation, what was u1? u1 was just 1, 0, 0, because I have no cross terms, right? So that's the value that maximizes that. That's the eigenvector corresponding to the diagonal matrix 7, minus 5, 4. But so saying that, so x dot u1 equals 0 is equivalent to saying that x1 is just equal to 0. Okay? So now if you think about it, that reduces this equation. We were saying that we were saying that x1 squared plus x2 squared plus x3 squared is equal to 1, right? That's the unit sphere constraint. But now if x1 is 0, then this goes away, and we're just left with x2 squared plus x3 squared is equal to 1. So now we're on that unit circle that's orthogonal to the x1 direction. OK. So on this set, so once we're restricted to this set, really the quadratic form is just get rid of, I can't cover things up the way I usually would, but get rid of this term here, 7x1 squared. And now you just have minus 5x2 squared plus 4x3 squared. So I'm just trying to maximize this two-dimensional quadratic form on the circle. And by the standard analysis, that takes place at the highest eigenvalue that's left, which is just 4. Okay? So the same analysis that we've already done tells us that this theorem works in the case where I don't have any cross terms anyway. It's pretty obvious. Okay, and where would this value take place? Where would this maximum take place when I have to be perpendicular, when I can't have any x1 component? Well, it'll take place exactly when I have 0, 0, 1. Okay, so that's the eigenvector corresponding to 4. All right, so now actually this example didn't quite match the theorem because it does, the thing that's tricky is that here I've got my eigenvalues. I really should make my diagonal matrix be 7, 4, minus 5. And I should think about 0, 0, 1 as being the eigenvector u2. So maybe I'll write something down because I've said a lot of words here. So the max of q of x, which is now just equal to minus 5x2 plus 4x2 squared plus 4x3 squared. Let's make that clearer. Is 4, and it's at what I'll call u2 now, which is the vector 0, 0, 1. Okay? And now if you actually constrained it one further, that you had to be perpendicular to both of those, then you would just be trying to maximize minus 5x2 squared on the values that are plus or minus 1. That's the only possibility, which gives you the same output, so you get minus 5. So it actually works even in that case. So now let's try to do the second example where we have cross terms. So if we have cross terms, then again we have to remember what the matrix is. So this matrix is still the same. It's still 1, 1, 3, 1, 3, 1, 3, 1, 1. The eigenvalues are lambda 1 equals 5, lambda 2 equals 2, lambda 3 equals minus 2. And they correspond to the vectors. So you remember this corresponded to the vector 1, 1, 1. And I think this corresponded to the vector, and then I have to multiply by 1 over the square root of 3 to make it normalized. This one corresponded to 1 over the square root of 2 times minus 1, 0, 1. But now the one I want is lambda 2 equals 2. So I need to do something to figure out what that eigenvector is. So, I mean, probably the simplest thing to do is just, compute the null space of A minus 2 times the identity. And that turns out to be the span of the vector 1, minus 2, 1. OK, so here's an eigenvector. You can easily check that this is an eigenvector corresponding to 2. And once I tell you what it is, it's just a question of seeing whether it matches the defining equation. And now you need to find the unit vector corresponding to this. So what's the unit vector? Well, the norm of this vector is 1 plus 4 plus 1 is 6. So therefore, the max of Q subject to norm of x equals 1 and x dotted with u1 equals 0 is lambda 2 equals 2, and it occurs at 1 over the square root of 6 times 1 minus 2, 1. OK. And now it might be worth doing this, like plug this in and just do a reality check and see if you actually get lambda equals 2 when you plug that in, right? So notice with these square root of 6's, each of these things is a quadratic term. So I'll have 2 1 over square root of 6's that I'm multiplying together. So I'll have 1 6 times everything, right? So it's always good to check. So Q of this is going to be 1/6 times, OK, so now what do I have to do? I have to take the square of this, so that's 1, plus 3 times the square of this, so that's 3 times 4 is 12, plus the square of this, that's 1, plus 2 times x1, x2, so that's 2 times minus 2, so that's minus 4. And then I have 6 times x1, x3, that's plus 6. And then finally, I've got 2 times x2, x3, so that's another minus 4. All right, so now let's just check. What do I get? I get 12 plus 1 plus 1 is 14, minus 4 is 10, plus 6 is 16, minus 4 is 12, divided by 6. So I get 12 over 6, which is equal to 2, and that's equal to lambda 2, check. OK? So that's how these things work. The hard work was really done when we did the principal axes theorem, and after that we could just leverage that to take quadratic forms, get rid of the cross terms, and use a very easy analysis of the coefficients of the quadratic form when it doesn't have any cross terms to get all of this out. And what's even better is that we're going to leverage this in upcoming lectures to prove the singular value decomposition. So I think that's it for video lecture F11. Thank you very much for your kind attention.